and periodicity in properties of elements class. So in a previous class, we have seen that um, different types of uh, uh, metals classifications in the main periodic table. Basically, we have known about the main periodic tables and how they have this element has been classified and which are the which element and what's the block SPD. Uh, so it is so about that we have learned in the previous class. So today we will know about the some periodic properties, some chemical properties and the physical properties. So in this class, what we will learn about that. First of all, we will learn about the shielding effect. Another thing, we will learn about the atomic radius and the ionic radius. So the periodic table in this periodic table, so the periodic trends in the physical properties. So first of all, we will talk about the physical properties. So there are the some physical properties. So among that, so shielding effect, atomic radius, and this ionic radius. So these three uh, physical properties of these element and what strength actually they follows that we will learn from that class. Another the physical properties like the ionization energy, electron gain enthalpy, and electronegativity we'll learn the later. So the periodic trends in the chemical properties. So these are the physical properties. These are the physical properties. Now, what's the chemical properties? Chemical properties means that the reactivity of that elements with this another uh, reagent. Okay. So basically, when we will talk about the chemical properties, then uh, the oxidation state of this element would be the change, and there are the some chemical reactivity also will be the change. Uh, some physical state also will be the change. Uh, so the when we will talk about the chemical properties, first of all, we have to know the oxidation state before the reactions and after the reaction. So we will know about that part also the later. So first of all, today we will know about the shielding effect. What is that? The shielding effect, or we can say it is the effective. Sorry, uh, shielding effect. Somewhere it is known the screening effect, uh, or it is a shielding effect, or it is the screening effect. Both are the same term, but what is that actually? That we have to know that thing. So screening effect and the shielding effect. That means when we will thought about the shielding and the screening. That means there is this screen. There is a screen is there. Okay. So this screen actually uh, has the some effect. Uh, has the some effect. That's why something is happening here, or something is happening here due to this screen, due to this shield. So this is actually still like a wall. Okay. So suppose here is the room number one, here is the room number two. But between this room number one and between the room number two, there is a wall, there is a screen. So due to this screen or due to this wall, there something is happening. For that, some properties also will be the change of this house. Okay. So suppose this is the house. Okay. So there is the room number one and this is the room number two. Between that two rooms, there is a screen or the wall. Okay. So some condition you can see this wall is more thick. Uh, some condition you can see this wall is the more bigger. There is the something is there. Okay. So due to the change of these properties of this wall, the whole properties of the some physical properties of this house will be the change. So like that, we know that about the atoms. Now compare now the come to the atoms. We know that atoms has the nucleus and it has the some cell like s orbital like so this is the nucleus always the positively charges, we know that because the nucleus has the proton plus the neutron. but the proton is always the positively charges and neutron the neutron. And there is the electron, which are always the negatively charges. Sorry again. So this is the negatively charges. Array, yeah. So what is happening here? Just give me 1 minute. Fix out this problem. No, will be the pair option. Okay. So what is happening here? So this is the proton and this is the neutron, and there is the electron. It is always the negatively charged. So for that nucleus, it is the positively charges, and the electron is the negatively charged. What is happening for that shielding effect? Suppose for that atoms, there is the one cell. First, this is the one cell, and this is the second cell. Okay. So in that second cell, there is the two electron. This is the electron, and there is the one electron. Okay. But in the first cell, you can see that there is the three electron. Okay. So this is the three electron. Now, this is the positively charged. This is the negatively charged. So there should have always a attractions between these positively charged particles and negatively charged particles. Like that, here also a attractions between the electron and this nucleus. Okay, so for that attraction, some amount of the charge will be affected on this electron. That is called actually nuclear charge. That is called the nuclear charge. But this nuclear charge will be for that atoms. There is the five electrons is there. The nuclear charge will be the five. But due to presence these three electrons, some amount of this charge will be increased or some amount of the charge will be the decrease on this outer shell electrons. Then it is called jet effective jet star. That is called the effective nuclear charge. That is called the effective nuclear charge. Now, so this jet effective nuclear charge, somewhere it will be greater than the jet, but somewhere it is less than the jet. So when this effective nuclear charge will be the increase and when this effective nuclear charge will be the decrease, that we have to know actually which condition. So for that, so just think about that. So there is the three electrons, there is the two electrons in the outer shell. So this is the inner shell and this is the outer shell. So in this inner shell, there is a three electron, there is a two electrons. So electron, always repulsion will be there. Okay, so this is the repulsion will be there. But this electron to this electron, attractions will be there. But what is happening here, due to this repulsion, between these two electrons, the distance of these two electrons will be the increase. The distance between the two electrons will be the increase. When this distance will be the increase, somewhere, suppose due to this electron repulsion, these two electrons is present here now. Okay, so this is the A distance, and now the distance is the A dash. So the A dash greater than the A. So distance is increased. When this distance is increased, then this attractions between this nucleus and these electrons will be the decrease. When this attractions will be the decrease, then the effective nuclear charge also the decrease. So what is happening here? The attraction, when this attraction will be the decrease, then the effective nuclear charge, this effective nuclear charge also will be the decrease. Okay, so so this is actually proportional to the attraction, but the disproportional to the repulsion between this electron. So so Z effective nuclear charge. So the effective nuclear charge actually increase due to this electron, Okay. So presence of this electron, somewhere it will be the increase, somewhere it will be the decrease. Okay. So that's why a decrease in the there is a some condition is that effective nuclear charge always with a decrease. So the decrease in the nuclear charge, the nuclear force of the attraction on the outermost shell's electron due to the repulsions caused by this inner shell electron is note that this is the shielding effect of the inner shell or the intervening electrons on the outer shell electron. Okay. So due to this repulsion, this nuclear charge is decreases. So this Z star will be less than the Z. Okay. So this actually effective nuclear charge is less than the need the nuclear charge. So this actually event is called the shielding effect. Okay. So this is the shielding effect. So now, so due to this shielding effect, so we know that this is a Z star or the Z effective equal to the Z effective nuclear charge. So the Z effective nuclear charge is star equal to Z minus sigma. What is that? Z equal to the nuclear charge. So this is a nuclear charge. But sigma is that shielding effect, shielding constant. That means that due to this inner cell, due to this inner cell, due to this inner cell, how much shield, how much this inner cell actually shielded this electron, uh, shielded this electron from this nucleus. That is called the shielding constant. So if we minus, if we remove this shielding constant value, how much shield is there? Okay, shielding constant value from that this nuclear charge, then we will get this effective nuclear charge. That's why a Z effective equal to Z minus sigma. This is a very important equation. So Z effective or the Z star equal to Z minus sigma, where the Z effective equal to effective nuclear charge and Z equal to the nuclear charge and sigma equal to the shielding constant. Okay, the shielding constant, that means the shield of how much it is shielded, uh, how much the outer shell electron it is shielded from this nucleus, or the how much this inner shell electron is shielding this outer shell electron from this nucleus. Okay, that's value if we know, then if you remove this value from this nuclear charge, then we will get this effective nuclear charge. So this value, this jet effective nuclear charge actually is affected on this outer shell electron. So So to determine this shielding effect, there is the some value is there. It is mentioned that if your principal quantum number, if it is your principal quantum number, equal to the one, n equal to the one, only there is a 1s orbital is there. Only this atom has a 1s orbital. Then this shielding effect, this per electron, this sigma value will be the 0.30. Okay, 0.30. That is the for this only for this one cell. Only for this one cell. But but suppose n equal to 2, your principal quantum number n equal to 2. So according to this principal quantum number, you will have this orbital 2s and this 2p. So for that orbitals, actually for this quantum number, this sigma value will be 0.35. Suppose n equal to 3. So 3s and 3p and the 3d. For that actually the sigma value will be the 0.35. But n minus 1, or that n minus 1 will be the sigma value will be 0.85. Okay. So in that way you have to calculate it the Z star or the Z effective sigma value. Okay. And the and then the then is that, so it is the most important thing is that we know that for an atom, there is a nucleus. Okay. Then the s orbital, is the p orbital, then the d orbital, and this f orbitals. Uh, so due to the shape of this s orbital is the fuse, and p orbital is the dumbbell, and d orbital also the dumbbell, but there it has the like that actually. F orbital like also that. So due to the size of these orbitals, and also the diffusion effect is also there. If you see the shielding effect strength of this orbital is s orbital has the greater shielding effect, then the p orbital, then the d orbital, and this f orbital. So when we will look for this f orbital, then the shielding effect is the very less. For the d orbital also the very less compared to the s and the p orbital. So s orbital, p orbital will show the greater shielding effect, greater the shielding effect than the d orbital and the f orbital. So so that is the thing actually here we have already told about. So this is the one example. This is the one example. Here we can see that uh, the Z value equal to 9. That means number of electron or the atomic number equal to 9. Okay. So when this atomic number equal to 9, then the electronic configuration will be 1s2, 2s2, and this 2p5. So here the maximum quantum number n equal to 2. So when n equal to 2, then so this 2s orbital will be the 2 electrons, and 2p orbital will be the have the 5 electrons. So total number of electrons equal to the 7 for this 2s and the 2p. So 2s and the 2p will be the 7 electrons. But when we are doing the calculation of this shielding effect, this is the sigma. What will be the sigma? Then we have to subtract the one electron, because this one for that one electrons we have to calculate it. So we cannot consider this one electron. Okay. So for that n equal to 2 or for that n equal to 2 principal quantum number of electrons will be the 6. So for that 2s and the 2p orbital, the sigma value will be 6 into 0.35 equal to 2.10. So this is the 2s and the 2p orbital. Now the 1s orbital. 1s means that's n minus 1. 2 minus 1 equal to 1. So for that case, the sigma value will be, so there is the 2 electron, so 2 into 0.85. So it will have 1.70. So total sigma equal to 2.10 plus 1.70 equal to 3.80. Okay. So now we know that Z value, we know that this Z value 9, and this sigma value is equal to 3.80. So if you subtract this 9 minus 3.80, so it will get, we are getting the 5.20 Z. That means that this amount of this effective nuclear charge is affected on this outer shell electrons. If you see, this is the 1s, and this is the 2s, and this is the 2p. So there is the 2 electron, there is the 2 electron, but there is the 5 electron. Okay, there is a 5 electron. So these 5 electrons actually affected by this 5.20. We do not know the what actual will be the arrangement of this atomic orbital, but you have to consider one less actually electrons, because you have to calculate it for this one electron. That's why you cannot consider this electrons also for that calculation of the sigma value. So that's why you have to took the 6 electrons uh, instead of the 7. So this is the one example. Here we can see that how the sigma value, this shielding effect constant actually this or the effective nuclear charge has been calculated. Now the strain. Now we will know about the trend of effective nuclear charge in the periodic table. Uh, how it is the trend? So you just think about that. Z star equal to Z minus sigma. We have to calculate the Z star, and you will have the value of the Z, but you have to calculate, only you have to know the sigma, this shielding constant value. Now, this shielding constant value actually dependent on the number of electrons. When this number of electrons will be the more, then the sigma value will be the more. Okay, and this Z value also will be the high. Suppose when this atomic number is increasing, when this atomic number is increasing, then Z value also the increasing. Then the sigma value also the increasing. But you have to know how much this sigma value has been increased. Okay, so if we abstract that value, then the Z star value we will get. So similarly, here you can see that in a periodic table, in a period, suppose we are going to the lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, so this is the three atomic number: 4, 5, 6, 7, 8, 9, 10. So this is the atomic number. So this atomic number is increasing. That means this Z value also the increasing. But Z value is the increasing. But you have to know the sigma value is increasing in the same strength. If the sigma value is increasing the same strength, then the Z star will be the similar. But here, if you see, there is the huge change of this Z star value. Uh, so between that, the change value is 5, 3, 0.35. This is also the huge change. Uh, this is also the 0.65 change. So mostly you can see that 0.65 is the changing. 0.65 value is the adding for that when we are going through this boron to carbon, carbon to nitrogen. That means that sigma value sigma value is decreasing when we are going to this lithium to neon. So let's think about that again. Z star equal to Z minus sigma. This value is increasing. Uh, this value also increasing. That means that this value this value is increasing in the same strength, and this value is increasing in the same strength. That means that this value is decreasing in the same strength. Okay, okay. That's why this value is increasing. When this value is decreasing, then this value will be the increasing. So that's why if you see when we are going to this lithium to the neon, uh, then this effective nuclear charge is increasing. But this shielding effect constant value, this is a sigma, it is the decreasing in the same strength. But why it is the decreasing? That is the question. Okay, why it is the actually uh, decreasing? That is the actual question. So the shielding effect is decreasing. So what is happening here? Shielding effect is decreasing. This the sigma value is decreasing. Now think about that. Why why it will be the decreasing? What factors actually on the what factors this sigma value actually the dependent? First of all, one factor is the orbital. S orbital, p orbital, d orbital, f orbital. S orbital will have the more sigma value. When we are going to this p orbital, when we are going to this d orbital, when we are going to this f orbital, then this value will be the less. So for that case, this lithium, only the s orbital is there. And for that case, no, sorry, there also the p orbital also is there. But for that beryllium also, there is a 4 electron. So 1 is to 2 is, sorry, 1 is to 2 is to s orbital. Sorry, here this 1 is to 2 is 1. Here is the 1 is to 2 is. So this is the s orbital. When is the going to this 5? Then 1 is to 2 is 2 and 2p1. Then the p orbital is coming here. Here is the p orbital. there is also p orbital. There is p orbital, there is p orbital, there is p orbital. So when this p orbital is coming, when this p orbital is coming, then this value also is decreasing. This sigma value is decreasing. But here, this s orbital is there. Okay, so that's why that s orbital is showing this more this sigma value than the p orbital. Uh, so if you calculate this value actually, then it will be the more clear for you how why actually this value is the decreasing. This is the calculated value. Okay, but there is the strength. There is the overall idea is that when this atomic number is increasing along the period, uh, when this atomic number is increasing, uh, then this value actually also the increase. But point is that, point is that the sigma value also the decreasing. The sigma value is the decreasing because the inverse of the p orbit. Now, if we go to this group, then this value is similar. The value is the similar. That means that z star equal to z minus sigma. Okay, when we are going to this group, uh, above to down, from this hydrogen to lithium, this sodium, potassium, rubidium, cesium, then the atomic number is increasing. Atomic number is increased. That means the principal quantum number 1 to 2, 2 to 3, 4, 5, that also the increasing. That means that this Z value is increased. When this Z value is increased, number of electrons is increased. And if you see all orbitals, the last electron is present is the s orbital. So here the s orbital is the constant, orbital is the constant. So this value also the increase. When this value is increased, then this value also the increase. That's why it will be the less. What point is that when this value is increased plus 5, then this value also increase this plus 5. So whatever will be the former value, now this value, the present value will be the same. Okay, so that's why here there is the no change of this the effective nuclear charge in a group. So effective nuclear charge in a group is not changing, but in a period, effective nuclear charge is the changing. So it is increasing, but it is the same. It is increasing, it is the same. So this is the strength of the effective nuclear charge in a group and in a period. So now think about there is a question is that so in a period, if you see the in a period, if you say this Z star value is the increasing, that means that effective nuclear charge is increased. So there is the nucleus, there is the electron, outer shell electron. So when this effective nuclear charge increase, that means that there is the attractions between this nucleus and this electrons will be the increase. When this attractions will be the increase, then the atomic radius will be the decrease. So this Z star is increased, but this atomic radius, for that case, atomic radius will be the decrease. But in a group, if you see in a group, this Z star value is the same. So the Z star is the same. Z star is the same. That means there is the nucleus, there is the electrons. When we are going through this hydrogen to lithium, lithium to sodium, potassium, rubidium, cesium, this attraction value, this effective nuclear charge value is the same. But what is happening here? The principal quantum number is the increase. When this principal quantum number will be the increase, then automatically the atomic radius value will be the increased. So here the atomic radius value will be the increased. So so this is my the second slide is that for that atomic radius uh, will be the increase. This is the thing you can just think about that. In a period, the atomic radius will be the decrease with this increase of the atomic number because the n number of the cell remain the constant. There is the n equal to the same. But when what is happening, the Z increases by 1 unit, Z star increases by the 0.65 unit. So electrons are the pulled close to the nucleus by the increase the Z star. That's why the atomic radius will be the decrease. That's why lithium has the 1.3, barium 1.95. Uh, sorry, sorry. Yeah, this is the value. This is the Z star value. This is the Z star value. Okay, this is the Z star value. So this is the strength you can see. This is the lithium, then the sodium, potassium, medium, cesium. So this is the actually group. If you go to this lithium to the fluorine and the sodium to this chlorine, this is the period strength. Here you can see this atomic radius for this lithium, atomic radius 152. Now this fluorine case, atomic radius is 50. So this atomic radius decreases. Similar case for this sodium and this boron, bromine. For this rubidium case, this atomic radius also that decreases, and cesium case, atomic radius also that decreasing. So this is the periodic. So this is the period strength. Uh, Now the group strength, if you can see that lithium to sodium, sodium to potassium, and the rubidium and the cesium, the atomic radius is the increase because the principal quantum numbers value is actually increased. So this is the strength. Okay. So here also you can see that in this group, this atomic radius is increased moving the down the group because n is increased, z also increase, but no dramatic increase in the z star. Almost the remain same. This is the z star value. Already we have seen in the previous slide that this hydrogen to lithium to sodium, potassium, rubidium, cesium, this value is not changes here. There is the no change of this z star value. But the principal quantum number is increased. That's why this atomic radius value also the increase. So this is the atomic radius value changing. Here also you can see that when we are going to this hydrogen to sodium, potassium, rubidium, cesium, then the atomic radius is changing. Okay, it is the increasing. This is corresponding to this period 1, this is period 2, period 3, period 4, period 5, period 6. So what is the conclusion here is that with this relation with this atomic radius, generally atomic radius is proportional to the Z star. When this Z star is increased, that means this effective nuclear charge increased. Uh, then the atomic radius will be the decrease. Uh, so so in the in the group, sorry, in the period, you can see that this is the period. So in this period, this atomic radius will be the decreases. Sorry, sorry, in this group, and this is the period up to down. It will be the increases. So this is the period. So when we are coming to first period to the second period, second to the third, third to fourth, then this arrow is actually the increases. But when we are going to this first group to the second group, then the fourth group, then the 8 number group, then the atomic radius will be the decreasing because the increasing of it of that the jet star had. Sorry. Um, just give me 1 minute. What is happening? Okay. So this is the case. So here you can see there is a different type of the radius. First of all, this metallic radius. Metallic radius is the half of the experimentally determined distance between the nucleus of the nearest neighbors in the solid. So when it is the solid state, when it is the solid state, suppose there is the two sodium is there. Okay. So when this two sodium is there in the solid state, so this distance is called this metallic radius of that sodium metal. Okay, so this is the metallic radius. Another is the covalent radius. So when a non-metallic element is a half of the experimentally determined the distance between the nucleus of the nearest the neighbors in the solid. What is that? So this covalent radius means suppose is we are forming this NaCl. Uh, This is the sodium, this is the Cl. So this is the sodium, this is the Cl. Na plus Cl minus. So it is forming a covalent bond. So the half of this covalent bond is called this covalent radius. Uh, so half of this covalent bond distance, it is called this covalent radius. And ionic radius means that there will be present these two ions, sodium plus and the Cl minus. Uh, so one is the cation, one is the anion. So there will be no the covalent bond. There will be the ionic bond. So this is distance. So this distance is called this ionic radius of that sodium, and this is distance the ionic radius of this 99 ppm for this sodium. So ionic radius of an element is the related to the distance between the nucleus of the neighbors, cations and the anions. So this is the ionic radius and this is the covalent radius. This is the metallic radius. And here we have known about this shielding effect strength, and uh, this is the periodic tense of this atomic radius in the period, and this is the periodic this is the in a group atomic radius is increasing, and this is also the one figure. Here we can see that when we are going to this hydrogen to lithium to sodium the potassium rubidium cesium, uh, when the atomic radius is increasing. So the conclusion is that when this atomic radius, when we will know about this atomic radius, then we have to know this effective nuclear charge value. When this effective nuclear charge value is increasing, then the atomic radius would be the decreasing. Uh, so along this growth, so the atomic radius is decreasing, but when the period on this period when we are coming to from the up to down, then then the atomic radius value will be the increasing. Now this is the ionic radius. This is a very interesting thing is that what will be the relations between the ionic radius and this atomic radius. We know that ions means anions and another is the cation. Suppose A is an element. It is a taking one electron from this other side, other source, then it is forming a anion. But when it is a giving one electron to this other partner, then it is forming a cation. So for that anions means adding electron, cations means it will be the opposite, removing electrons or abstract electrons. Okay. So anions means this adding electrons. So where these electrons will be the added? These electrons will be the added in the outer shell, and for the cations, electrons will be the removed from the outer. So for that anions, one electron is the extra. For the cations, one electron will be the less. So for the anion case, the effective nuclear charge, the shielding, this shielding actually this sigma value will be greater, and here the sigma value will be the less. Uh, the sigma value when it is the increase for this anion case, then the Z star value, this effective nuclear charge value will be the less. For that case, effective nuclear charge value will be the increase. So it is written here because the addition of one or the more electrons would result in the increase the repulsion between the electron and decrease the effective nuclear charge. That is actually happening here. When we are adding this one electron from that other side, other source, then there will be the repulsions between these electrons. When this repulsion will be there, then 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 the distance, the atomic distance, atomic radius also the increase. Uh, and due to this repulsion, the J star, this effective nuclear charge value on that electrons will be the decrease. When this effective nuclear charge will be the decrease, then the atomic radius, then the atomic radius, sorry, the ionic radius for that anion will be the increase. So again, the J star is proportional to this ionic radius. Okay, when the J star will be the increase, when with the increase, then the ionic radius will be the decrease for the cation. But for this anion, the J star value actually the decrease. So the ionic radius will be the increase. Okay. So again, because it has the fewer electrons still while it is a nuclear charge that remains and the same, or the this effective nuclear charge is the getter in the cations in the parent atoms. So if you see, this is the Cl2 actually. To chlorine are the covalent bond radius 99 ppm. When this two electron is given, then electron repulsion will be there. When the electron repulsion will be there, then the effective nuclear charge will be the decrease. When this effective nuclear charge will be the decrease, then the ionic radius value will be the increase. That's why it is the 99. Here it is the ionic radius 181 ppm. Okay. Now for the cation, for the sodium, it is the 186 ppm. For the magnesium, it is the 160 ppm. So when it is the removing one electron, then it is forming the sodium. When it is removing the two electron, then it is forming the magnesium plus 2. So when the electron is removing, then the electron repulsion will be the decrease. When this electron repulsion will be the decrease, then the Z star value will be the increase. When it is the increase, then the atomic radius value will be the decrease. But here, the two electron is removing. Here, one electron is removing. That's why this value is lower. 72, and this is the 99. So there is the another trend. So with that concept, we can also see that for that isoelectronic species, when the atoms and the ions which contains the same number of the electrons, then these are called this isoelectronic species. Like the fluorine, sodium, magnesium, it has the negative charge, it has the positive charge. Sorry, 1 minute. So here, these are actually the isoelectronic. Fluorine minus sodium plus magnesium plus. Fluorine minus sodium plus magnesium all have the same number of the electrons, is the 10. That's why these are called this isoelectronic. But when we are going to this each of this isoelectronic species, it is saying that it is decreases with this increase in this nuclear charge. What is happening here? So when it is a isoelectronic, just think about that. When it is a isoelectronic, that means that number of electron is the same. Okay, so the number of electron is the same. That means that sigma value also the same. Sigma value also the same. The Stirling constant value is the same, no? Of this fluorine minus ion, sodium plus ion, magnesium plus ion. Because for that fluorine, this cation and this outer set electron has the 9 electron. For that sodium also, there is the 9 electrons. For that magnesium also the 9 electrons. So that's why this sigma value is the same. But this Z value is the different. Okay, for that fluorine, Z value is the less than no sorry greater than that is sodium and the magnesium. That's why when this Z is the more, this is the same. So the Z star equal to Z minus sigma. This is the same. But when it is the increase, then the Z star will be the increase. When the Z star will be the increase, when the Z star will be the increase, then the radius value will be the decrease. So that is actually happening here. This is the size actually decreasing. For that oxygen, jet star is the size actually decreasing. So this size actually decreasing, that means that uh, so for that case the size is high. So this value is the size is high, that means the jet star is the very very less for that oxygen case. But the fluorine and the neon, sodium, magnesium, aluminum, so this value actually, this value is for that neon. This actually Z value, this Z value is increasing now. So when this Z value is increasing, uh, the size is actually decreasing. So aluminum plus 3 has, if you say this aluminum, this is the aluminum plus 3. Uh, this is the fluorine minus 1. Uh, this is the magnesium plus 2. Okay. So if you compare this fluorine and this magnesium plus 2 and the aluminum plus 3, then the fluorine has the greater atomic radius than the uh, magnesium plus 2 and then the aluminum plus 3. Okay. What is happening? If you see the number of electrons is the same, eh, and both are the both these are actually positive and this is the negative. So this is the no factor. Isoelectronic, that means the number of electrons is the same. There is the 10 electrons. But point is that this is the F value. Uh, this is the F value. This is the Z value. This nuclear charge value. This is actually nuclear charge value. Now, for that fluorine case, nuclear charge value is the 9. Uh, and this magnesium and this aluminum, it will be the boron case, it will be the 5 at the 13. It will be the 13, and magnesium it will be the 12, and this is value the 9, the Z value. When this Z value is the very less, then the Z star will be the very less because the sigma is the same. Sigma is the same. So the Z star will be the very less. That case also. So Z star will be that 10 actually. This is the Z star. When this Z star is the very less, then the atomic radius will be the high. That's why this strength actually, the size of the state is following that in that order. Okay, because the oxygen, if you see that oxygen has also the Z is less, is a 8. Okay, so that's why the Z star will be the very less. When the Z star will be the very less, the atomic radius will be the high. So this is actually for that isoelectronic case. So for that isoelectronic case, you just remember that this value is the same. So you have to calculate that value Z star equal to the Z minus sigma. So Z star value will be dependent on that Z value only. Okay. So this is that. And there is a some note is that metallic radius in that third row D block. So when it is going to this D block at the similar to the second row D block, but this not larger as one had expected, given there the large number of the electron. And there is the lanthanide contraction. So this actually comment we will talk about and we will discuss in the next class. So today here I am going to stop my class. Sir, we will learn about that in the next class. Thank you very much.